everyone, welcome back to Sun Innovative YouTube channel, and we are back with a new video on speed estimated direct torque control DTC for the induction motor drive. So of course this video is on a induction motor drive. So we are going to discuss the today regarding the direct torque control using the speed estimated technique. So in this video we will start with the first of all block diagram. So here you can see this is the general block diagram of speed estimated DTC induction motor drive, and the right hand side you can see the table is there, and in which the many methods are mentioned here for the drives. So there are the advantage and disadvantages also there. So first we talk about the DC drive. So you can see here the torque control is a direct mode and flux is also direct, and response is also high, and accuracy you can see it is a simple response. And if you find the disadvantage, so there is a maintenance cost is high and encoder is required for the higher accuracy. So these are the advantage and the responses of the DC drive. So now what is actually the direct and indirect control? So it means that when you have some parameters which is able to directly control, like speed is relevant to the torque, but if you are going to change the speed, so it is inversely proportional with the torque. So it means that you cannot have the control directly on the torque via controlling the speed. So in between you have to put some technique. For example, we have the block diagram here. So we are doing the dealing with the torque here. So after dealing with the torque, it means that there is a relational between the speed as well as the torque developed by a motor. So it's mean that you are also able to change the flux quantity as well as the speed quantity relevant with the torque. So actually for doing this you need to have the knowledge about the torque control and the relation between the speed, torque and the flux, because they all are connected with each other. It means if you are going to change the some parameters of induction motor, that will change the other parameters too. So it means you have to one intermediate quantity which can be relevant the two different quantity like flux and the speed, so you can easily control your induction motor drive. So let's start with the block diagram here, and if you move to the here the table, you can see the direct torque control is there. So in which you can control the torque by direct, flux is also direct here, response is also high, and advantage is there is no encoder is required and for the higher accuracy, and disadvantage we see that is a encoder required for the higher speed accuracy actually. So there are the advantage and disadvantage, both are same, because the both techniques can be implemented for the induction motor. If it is okay if you have the moderator as a accuracy improvement by using the encoder, and if it is also okay if you don't have the encoder for the induction motor. So you see here the block diagram is here. So first of all we start with the speed command, you can see here, and the command is given to this error block, and the actual speed is measured by this line, and whatever the error is generated it goes to the PI controller, and the whatever the estimated speed is generated it goes to the torque command. And one more torque hysteresis controller is connected, and similarly for the speed like flux is also there, you have to provide the flux command here, and it will also measure the flux quantity by using the stator flux and torque estimator here. So it is a block is which is important to have the knowledge about the flux and torque, which is measured by the induction motor voltage and current values. So it will capture the present values of stator flux and torque, and it will also going to compare with the reference which we have given by the users, right? So these both are a hysteresis controller here for the flux and the torque for the individually, and the whatever the error is generated that will be going to the optimum switching table here, and this will select the vector control and the switching for the inverter, so that PWM pulse is given to the PWM inverter, and whatever the output voltage is generated from the inverter that will be given to the induction motor. So now what we do in a simulation, we will step by step see the function, and we will start with this block diagram, and I will show you that how you can do this simulation, right? So if you see the more in a detail, that suppose if you want the equation, so there is a equation is also there, so you can see right hand side is there. So you see here the inverter is there, and the voltage and current you can measure from this way, and whatever the estimated voltage and current will be given to the Park transformation. And the equations is follows here: the flux for the alpha and beta values, and the developed torque from the motor that will be given to the reference value, and the PI controller for the torque and flux individually, and that will be gives to the V alpha and V beta for the stator, and this is the space vector modulation, and the pulses are generated that will be given to this inverter. So by this way you can change the reference value from the speed value here, and you can able to control the motor speed. So in that case you need to assume this following drives advantage here. So in direct torque control you can see the motor torque and motor magnetizing flux that you need to control in this theory. So mainly we are focusing on the torque and flux only, so that we going to show you in this simulation, right? So we are starting with the simulation first of all. So let's come back to the theory again. You see this is the speed command, and we need to develop the speed controller here first. So we have the speed command here, you can see in a green side, and this is the summation block, so you can compare the actual and the reference you have given to this system, and whatever the error is generated that will be given to the flux estimator, speed estimator here. So you can see this is a speed estimator, and it is nothing else, it is a PI controller only. And let's go back to the theory again. So you can see here that signals goes to the torque command here, and you need to parallelly develop the flux command here. So you can see this flux command here, and whatever the torque is developed that will be given to this hysteresis controller for the torque as well as the flux controller. So let me open the theory again. So you can see here the flux and the torque hysteresis controller is required, and whatever the output it's getting from the hysteresis controller, it goes to the optimum switching here. So that is given to see this one optimum switching table is also there, and the switching table is also required a flux selector. As per the theory you can see the flux sector selection is required for the switching table, and it will give the command of angle. It means in which sectors your PWM pulses should be operated, and it is also decided that when the flux is required to get increase or decrease. So that will be decided by the flux selector here, and this one is a flux and torque estimator as per the theory, and this is the inverter, and the output voltage is given to the induction motor. In a previous video we have seen the modeling of induction machine that I have already used this file in this DTC control. I also explained all the blocks from the previous video, so you can find the link in the description and the icon button from the video, so you can find the introduction about the induction motor modeling, right? So now I am taking the measurement from the omega for the reference here from this way, and I am also going to control the load torque from by using this slider gain. So I need to show the each and every block right now. So first of all I will start with the three-phase inverter. So I am going to measure the VAN, VBN and VCN from this block, and I am taking the measurement as a VABC and IABC, and I am giving to the flux and torque estimator by this way. So this is the subsystem of flux and torque here. So you can see the equations are there. So if you want to calculate the flux for the stator, so you need to follow this equation as per the theory, and if you want the same the alpha and beta value for the stator flux in a terms of D and Q, which is actually Park transformation, so you need to follow this equation, and in which you can see there is a ISD for the direct and quadrature axis for the current and voltage. So U it means voltage for the direct and quadrature axis. So you have must this block. So you can see this is the block which is give you the Park transformation VABC to the alpha beta for the voltage for the current, and the all values are given to this flux estimator, and this is the function for finding the flux by using this equation. So same way you can find the stator flux by DQ method, and this is the developed torque, which is equation is also mentioned here. So you can use the basic component from the library and you can develop this equation by using this equation. Okay, so now this is the nothing else, this is a subsystem for flux and torque estimator using Park transformation. And With this block we are getting the values of flux for alpha beta values, developed torque and the flux, right? So that I'm taking the outside, and you can see this is the psi s, it means stator flux. I'm not able to put the symbol, so that's why I'm writing the name here, and that link is given to this my reference hysteresis controller, and the whatever the torque is there also, it is from coming from the measured value from the induction motor. So that is also given to the speed estimator here for comparing the reference torque which we have developed from the speed reference, right? So now I have the value of alpha and beta that goes to the flux estimator. So you see here the flux sector selection is very important, because you can see this table that will going to decide by this switching table that, and at which point your flux should be increased and which point your flux should be decreased. So in that case you can see the relevant parameters, that is a torque, it is also required, because both are interconnected with each other. So it means that in during 0 to 30 degree you need to control have the torque and the flux increase. So by this way you can able to generate this sector estimation, and you can also find out the switching table. And if you go to the theory, so you will be easily understand that how to design the flux sector selection, right? Now from this block we are giving the command to the optimum switching table. So I'm opening this block here. So you can see the optimum switching sector will give you the vector control here. So it means that if you wanted to run your in a sector 1, so in between sector 1 you have the control on a flux by this 6 switching table. So I have prepared here the looking table here. So I'm opening this lookup table for you, and this is the lookup table actually. So I have designed this one, and I'm giving the PSI sign value here by using the vectors values 100, 001, and the 8 different searches table is there. Okay, so you can do the same for the program. So if you are not able to do this, please write in a comment box, I will help you to design the lookup table. So it will select the values of the vectors which is required by the sector 1 and sector 2. So after selecting the sector, it will goes to the further flux control switching table. So this is the switch selector actually. So there are the 8 states are there as per the vector control. So it means that it will give the 8 parallel switching pulses to the our inverter, so that it can generate the output voltage as per the sector selection, right? So pulses are given to this inverter, and the whatever generated voltage is goes to the induction motor. So now I am going to run this simulation. This is enough for the theory and explaining the all connections and diagrams, right? So this is a large project, so I don't have much more time to explain each and every point in a detail. So if you have the question, you just go to my website and follow the instruction, and there is a blog and forums is also there. You can write your question and you can ask any type of question, so we will try to help you the question and sort out the all queries, right? So again I'm opening the theory here. You can see you have to follow this switching table, a block diagram, and develop this speed estimator DTC. Now I am running the simulation to show you the result. So now this is the simulation. So I'm opening the scope here. So you can see here the first graph is a motor developed torque, and second it is motor speed, right? And I wanted to change the speed reference and as well as the load torque to show you that what is the importance of DTC here. So that I am going to explain you right now. So now by using this theory, I have to prove that what is the importance of when we are changing the speed here. So I'm getting the result right now. So I'm using the slider gain here. So you can see this speed slider gain, and this is a load torque slider gain. So now I'm running the simulation again to show you that what is the impact of speed and the torque when we are changing the slider gain values. So here I am taking the values. So first of all I am changing the torque here. So you see here the 14 and minus 14 values is there. So if I am changing the torque here like this way, so you can see now torque is changing here, but in that case you can see the speed is doesn't affected, and this is the actual design which we required. It means that when load is connected or the increasing the load will not going to affect the parameters or performance of induction motor. So further I am changing the load torque here. You can see if I am changing the load torque, and you can see the steps values are given, but there is a no change in a speed motor, right? So this is what we required here. And if you further decrease the load here, so you can see the minus torque is developed because we have provided negative 7 point Newton meter, but in that case also the speed is not going to change. So this is what we required in an induction motor drive. So when we are changing the something values, so it should not be affected. So this is what we required in a design. So in that case also, if we are changing the speed also in that case, so what is actually requirement? So you see here, when we have the values of torque here, so you can see, and when we are changing the speed command, so torque should not be changed the values. So this is what we designed the speed reference, you can see. And if I am increasing the speed again, wait 1 minute, so this is the negative value because we have changed the speed and the load torque. So I am again resetting my values here. So you see here, this is the speed values. I need to stop the simulation, there is an error, so I need to run the simulation again to show you the speed effect. And you can see now I wanted to change only the speed values and the quantity, so I am changing the here. So you can see, so now I have the value of 53 here. So in that case I change my values, so there is no change in a torque, and again I am changing my values of speed. So you can see now it is increasing, but there is a no change in torque again. And once more if I increase the value of speed here, so there is a no change in a torque right now. So same way if I reduce the speed, so now you can see the speed is reduces, but there is a some little jerk is there, but there is a no change in a torque. So it means that your motor can smoothly if you are changing even speed quantity by varying the speed reference, right? So this is what the direct torque control is there. It means that there is a proportional to relation between the speed and the torque. It means one of the quantity is going to change, so at that time the other quantity should not be change the performance. So this is what the actual performance of the DTC, right? So I am opening the here the reference for the torque and the actual. So black line you can see the actual measured torque, and red line it is the reference which we are given. So you can see the nearly it is operated in a reference value. So this is what we have required. So again I am showing you the reference here by changing the torque again. So you see here that I am taking the slider again and I am changing the torque values. You see our torque will follow the our reference value. So it means that I can have the control on directly of the torque. You can see in easily window that again I am reducing the torque value. So my actual black line should follow the actual torque, and red line it is my reference value. So this is way you can follow your load torque by this way, changing the step values. And my system is working fine right now. You can see if I am changing the torque, my actual value is also going to follow the red line as per the direct torque control, right? So this is what we have the direct torque control on a system by using this speed estimator technique. So in that case also I am going to show you the voltage and current here. So I am zooming these values. So you can see here the current is changed here. You can see in that case the magnitudes are changed here. The little bit you can see the reference values are changed for the torque. So that time your current is also going to change because torque is relevant to the current. So you can see the magnitude difference is also there. So this is why, because we have changed the torque, so that's why the current is also going to change. So this is all about the speed estimator direct torque control, and we have proven that if we are changing the direct torque here for the reference, so that time speed is not going to change. So this is what we required in AC motor drive, right? So this is the simulation of speed estimated DTC induction motor drive, right? So thank you guys, thank you very much for watching this video, and please share and subscribe this channel.